So our next speaker is Plawan from the Chennai Mathematical Institute, and he will talk about uniform versions of the Shafarevich conjecture.
Okay, the title of the talk is Uniform Versions of Shafarevich Conjecture. So first I will state what is Shafarevich conjecture, and then we'll see the generalizations. So yeah, so let K be a number field, K bar be an algebraic closure of K, and Gk is the Galois group, and these are Z, N, M, and these be positive integers in my talk, and L be a prime number, and S be a finite set of places of K which contains, I'm assuming that in the whole talk, S contains S infinity. Okay. And by the notion SL, I will denote that all the places S union, all the places of V lying above L. This is SL. Okay. And F will be a non-Archimedean local field or characteristic 0 and residue characteristic L. Okay, so we have this famous Shafarevich conjecture, which was proved by Faltings in '83. So given if you are given the number field K, a positive integer Z and S, then there are only finitely many isomorphism classes of abelian varieties defined over K of dimension Z, and which have good reduction outside S. Okay. So if we fix the bad places, then there are finitely many bad places, number field K and Z, there are finitely many abelian varieties up to isomorphism. Okay. The similar finiteness theorem we have the Hermite-Minkowski theorem. So if you fix, similarly, if you fix the number field K and a set of bad places S, then the field extensions of K, which are ununified outside S, and then we have to fix a degree also. If we fix the degree and a degree is less than N, then there are finitely many extensions which are ununified outside S with bounded degree N. Okay. And then okay, and this finiteness theorem, again, then we have then Fontaine's theorem, which says that there are no abelian varieties which have everywhere good reduction defined over Q. So if you take K equal to Q, the rational numbers, and S equal to just empty set, then Fontaine's theorem also says that there are actually this set collection is empty. Okay, then yeah. And these theorems, again, we have for elliptic curves also. So these theorems for elliptic curves, that there are finitely many elliptic curves if we fix K and S. This was proved by Tate. And then this theorem also that there are no elliptic curves defined over a number field, which has a defined over Q, which has everywhere good reduction. This is also proved by Tate. And then in the proof for elliptic curves, they use the fact that S integers are finitely many and finitely generated, and then it boils down to solving some equation, means that is the Weierstrass equation of the elliptic curve over the S integers, and S integer solutions are finitely many, means using some Ziegel's bound or Ziegel's lemma, means. So those proofs are little different, and then the proof Shafarevich conjecture, the Faltings, the proof of Faltings goes by means it use Tate conjecture, it relates abelian varieties and the corresponding Tate modules, means somehow this is related to finitely many means finiteness of isomorphism classes of Galois representations that we will come to the next slides. Okay, and yeah, and this is also, from this also we can get that if you take Z greater than equal to 2, then yeah, Z greater than equal to 1 also, yeah, then finitely many curves of genus Z, which has good reduction outside S. This also can be derived from this. So means if you take the curves, then if you take the Jacobian, then if curve has good reduction, then Jacobian has good reduction, means. But the converse is not true actually. Means the these good reduction properties, if the elliptic curve has good reduction at some place V, then the corresponding representation has good reduction. The cohomologies had good reduction. That is the Neron X Shafarevich criteria, and that was for abelian varieties that was proved by Tate, means. Yeah, so you have if abelian variety has good reduction, means at a place P, then I just want to say, yeah, if A is defined over K and A has good reduction at V, means at a place P, and some equivalent criteria, then we have the state module representation AL. This is defined as you take the L power n torsion points. This is over k bar, and take the inverse limit over n, and then you tensor to it QL. Then this will be a 2Z. This gives a 2Z dimensional QL representation. Okay, that means I'm just saying that GL 2Z QL. Just fix a basis, and this will be isomorphic to GL 2Z QL. So what Sayre Tate article says that A has good reduction at B, then this is ununified at B. So for L O prime 2 residue characteristic at P. This statement is also equivalent to, if you take this extension to attach these points or some n, means A, this is ununified at the places P, not dividing n. Okay. So this equivalence. So in this talk, this equivalence also I am going to use. Okay. This is the Neronog Shafarevich criteria. For elliptic curves, yeah, Neronog Shafarevich proved this, and for abelian varieties, yeah, Sayre Tate's proved this. So yeah, now I will go from so I'm saying that later I will come, means this conjecture is related to equivalence of Galois representations, finiteness of. So we have this in the faultings theorem, means faultings. This is we have a criteria of faultings that which says any two elliptic representation means any two representation. If I take rho and rho prime, means these are from ZK to GL and QL. So we know that these are characteristic zero field. So if characters are equal, then representations are equivalent. Then the thing is that using Sabatorov density theorem, we can say that if these representations are ununified outside S, then some particular elements, it is enough to check the equivalence of the elliptic representations on a particular collection of elements of ZK. Those are the Frobenius elements. So if I say that means characters rho L at the Frobenius elements, yeah, trace of rho L of Frobenius P is equal to trace of trace of rho L prime of P for P. Yeah, ununified outside S. Yeah. But we can say that if we have a dense collection of set of places, means this I can have a means I can say that P belongs to a dense collection T, which is disjoint from S, where T is disjoint from S and T is dense. Okay. So if this represents an equivalent, it is enough to check the representations, the characters are equal on a dense set of places. Okay. And then what the thing is there, the faulting, actually faultings try to find this T, finite T, is if it is enough to check the representation equivalent on a finite set of places T. Can we find a finite set of places T? And this was the main theorem of faultings, that this is the finiteless lemma is used, Faltings use this finiteless lemma in the proof of Shafarevich conjecture together with this one more fact he used. I will come to that later. But this is the more, to prove this, the Faltings, we need the Hermite-Minkowski theorem and Shafarevich density theorem and a clever use of Nakayama's lemma. He used and proved that argument, the first one. If the characters are equal, then the representation are equivalent. And note that if you are given K, S, F, those quantities, then there exists a T. That T doesn't depend on the representations, means clear from the sentence here. So if you given a K, S, then we already have the T. And now if you want to compare two representations, means it is enough to compare from that T. And with Rajan, we generalize this statement, means we just modified the methods what faulting used. The faultings proof we tried to method and we got this statement. And then here I am saying that in place of means, so this is, so now I want to talk about potential equivalence of representations if rho 1, rho 2, means I say that these are potentially equivalent if these are equivalent restricted to some subgroup of GK, GL, okay, L over K finite. Okay. So some equivalent criteria means for any Z in GK, there exists some M dependent on this Z, in such that if I say rho 1 of G power MG, these and these are equivalent. This element is conjugate to rho 2G MG. This I am calling element-wise equivalent. Element-wise equivalent. And then the traces of means traces of M powers are means that I am calling M trace. M trace equivalent, and these are potentially equivalent. Okay. 1, 2, 3. And then we can show that these and these are equivalent. These are this statement and this statement. These are equivalent statements for any the representations are. Oh, sorry. What happened? Okay. Okay. Yeah. So. Okay, the statement is missing. Yeah. So if M trace are equivalent, then the representations are potentially equivalent. For this, representations need not be for any field. Means there are GL and QL, local field representations are defined by local field. But if you take any field, then this statement holds. And these three are equivalent. These three are equivalent if we are working over a local field. Okay. So yeah. Okay. So here also using the results of Rajan and Patankar, so we can have a statement like this. There is a density, upper density one set T on where if traces of Frobenius are equal, then M power traces are equal, then representation are equivalent. And we modified that result of Rajan and Patankar, which says that there exists a dense set T. We make this dense set from to a finite set using this Faltings theorem. And then yeah. Yeah, if there exists the M. Yeah. Yeah, there's a recipe. That M actually depends on only the L, the prime L, that is the residue characteristic L, and the dimension N. There is the M like that. Okay. And here I am not use that inertia can act by M order of the inertia, so order dividing M. Okay. I should not assume that representations are unramified. Okay. So here I am not assuming that even representations are finitely ramified. Okay. Even for infinitely ramified representations also we can use. If the representations are semi-simple, then okay, this criteria I am giving only for trace, that semi-simple representations. Okay. So if the representations are semi-simple, then Khade Rajan one theorem is there, the ramified places, the places where it is ramified, those are density zero set actually. Okay, so that we can use. Okay, taken much time. So Then because then using these theorems, we can have a finiteness theorem like Shafarevich conjecture. So but here we are getting up to k-bar isomorphism. Okay, because representations are potentially isogenous, and using Tate theorem, I will get up to potential isogeny, and then using this result by Bost, this is because Falting's theorem, they measure and Woolsholz give a different proof of that statement, that k-bar isogeny classes finitely many k isomorphism classes. For k-bar isomorphism classes also this statement, and using this I will get this for up to k-bar isomorphism there are finitely many abelian varieties. Okay, and here the earlier theorem I will use as m equal to 2. Okay, because m is 2 there, because for representation inertia image these are characteristic polynomials are defined over z actually, so only units are plus minus 1 there. So then I am now considering for what abelian varieties we have this criteria holds. On bad places it is means bad reduction property, where the bad places use act by plus minus 1. Okay, so this is the case actually. If you take, means here we have the Sevely decomposition. So here I am saying that means this this connected component A naught, this is just affine group scheme. Okay, then I will call it a totally bad reduction. For elliptic curve, totally bad is same as bad reduction. Okay, and then additive reduction is same as, means this is ZA there, and this is same as additive means that purely additive reduction. Okay, if you take abelian varieties, additive reduction is purely additive reduction, and this is just bad reduction. Okay, so for these special classes, we can show that inertia act by plus minus 1, and this used by one Lenstra-Wood condition, that with these conditions, the inertia fixed vectors of the Tate module IV, inertia fixed vectors of the Tate module, that is there's no inertia fixed vectors of the Tate module. Means I'm just saying with this condition, IV, this fixed vector, this is empty actually. Using that, we will get this actually. So I'm just hurry. So summary, this I am to summarize that what we're getting actually, we're heading the bad places. What kind of bad reduction? Actually the potential bad reduction. So if we're talking about the k-bar isogeny class and k-bar isomorphism classes, one observation is that the abelian varieties, if two abelian varieties are k-bar isogenous, the bad places where the inertia act via quasi-unipotent matrices, those are fixed actually. What happens is the inertia where the inertia image is finite, means those can be after base sense can be 1. Okay, what infinite image, it remain infinite. Okay, so if it is inertia act via quasi-unipotent matrices, the places where inertia act via quasi-unipotent matrices, means infinite order, those are fixed actually on a k-bar isogeny class. This is one observation. And then what we have proved actually, this is the one, just a summary of that. Means we have proved that the k-bar isogeny classes are finitely many here. So we are fixing S and S prime we are varying. And what is the X here, X bar? That is just finite by Falting's theorem, because outside S prime it has good reduction. So these are finite, but this is an infinite arbitrary union. Okay, I'm saying that this union is also finite. It's just rewriting this thing. Why I'm writing like this? Because of this conjecture. So this is this arises due to a question of Ihara. Means Ramanujan and Tamagama, they considered this collection AKGL. Means so these are the collection of abelian varieties k isomorphism classes where this is a L extension. We know that means by the well pairing, means so if you take the elliptic curve in place of k, then that contains the k mu L. Okay, for abelian varieties also this is true. And and then if this is a L extension, means somehow this kind of abelian varieties, when this is a L extension, these are rare in. So actually motivation is they want to find some curves in a Ihara tower. So I'm not explaining that properly, but so if I take any curve, then it has good reduction outside L. Means if you take the Jacobian, then this will be in this actually. Jacobian will be abelian variety. So for what curves, the Jacobian of that curve satisfies these properties. Okay. So so this conjecture is proved for k equal to q and g equal to 1, means, and that is for k equal to q and g equal to 1. This is related to means this condition is actually equivalent to for k, q, and this g equal to 1. having a L isogeny defined over Q, and using the Mazur's theorem, they proved that actually. And they conditioned this AKL over K mu L is L extension. This is actually equivalent to say that if you take the rho AL, the representation elliptic module, if you take the rho AL semi-simplification, rho AL bar semi-simplification, that is actually isomorphic to direct sum of powers of cyclotomic character. This is the this statement, means that related to this. And then we have this, these are other versions we have proved. And then what we're using here now means this is the result, means if it is abelian, rho AL is abelian, then the conjecture is proved by Ozeki. And then if we have, because what is happening outside L, it has good reduction. The thing is that above L, what type of bad reduction it has. So case by case, many proofs are there. So above L also, if it has good reduction, that is the potentially semi-stable case or semi-stable reduction, then this conjecture is already proved. Okay. So now what we did is we considered this collection that abelian varieties which is everywhere means totally bad reduction. Okay. Is either good at any place P, either good reduction or totally bad reduction. We take this collection of abelian varieties and try to say this conjecture is true for this type of abelian varieties or not. Okay, for here we have taken any K and Z. Okay, but we are restricting the class of abelian varieties. Then we consider that Ramanujan hypothesis that is satisfied by, actually after if you make the base sense KA12, then the Ramanujan hypothesis are satisfied over the base sense KA. Okay. And then we know this Reynolds criteria that over KA12, it has everywhere semi-stable reduction. Okay, and above L means we know this actually means if it has semi-stable reduction at places U dividing L, then Elliptic homology also it is semi-stable using this Fontaine's definition of semi-stability. Okay, these things we have, and then what we get is this statement: if K is a number field and Z is any positive integer or sufficiently large number L, we can say that this. Okay, and then for finiteness, this is empty. For empty, I can say that K isomorphism classes are empty because K isomorphism classes are empty if and only if K bar isomorphism classes are empty. Okay, so but here, but for finiteness, if you take the union, only we can say up to K bar isomorphism. Okay, so now if you take the Ramanujan conjecture, if we intersect this with AKZL, because we can show that this in the base field level, if we have a L extension, after base sense also it will be a L extension actually. That's why we have this containment. So for this collection, we have the Ramanujan conjecture is true. It is a very special class, means above L only potentially crystalline is allowed. Okay, in general means it is potentially semi-stable. So it's a very special case of even potentially crystalline also. Just there, yeah. But the thing, the whole philosophy, the thing is that if we have good reduction at every places P, means if we locally base sense, quadratic base sense, we will get good reduction. But we may not get for the all abelian varieties in this class, we may not get a uniform extension. Okay, then Falting's kind of theorem we can't use actually because we don't have abelian uniform LX field L, such that we base sense to L, everything has good reduction. Okay, that's why we have to go to K bar isomorphism classes. Okay, so to do this actually we have not the proper generalized, but the compatible system definition we have just little means we have sensed that in the compatible system means so we know that elliptic representation means a collection of elliptic representations. I will say it gives a compatible system if this is act by identity. This is identity for V not dividing this. So here I am taking this is dividing, this has order dividing M. Okay, and then so basically what happens is if we have abelian varieties which has potential good reduction, okay, then actually here the motivation is S. Inside S I am taking all these places, means if I want to write this for abelian varieties, okay, actually the main motivation is the first, if we take S, outside S means it has potential good reduction. So all the places where inertia act by quasi-unipotent matrices, that I put inside S, and then outside S actually this will be satisfied. Okay, this will be satisfied. So what happens is by Reynolds means Ka12 over K means the previous side. This is a Ka12 over Ka12. This is semi-stable reduction, and yeah, already time is up. Yeah, so this degree is actually defined this dz. Okay, this is a one observation, and see that the dz doesn't depend on the field K and A. If we vary, then dz number is fixed. Actually, then we get the dz compatible system. What is the motivation for? Yeah, the second observation is the one of the motivation that in a k bar k isogeny class of abelian varieties, this will give me equivalent equivalent compatible system. That means for all L means abelian variety, I can take replace the all representations with a isogenous abelian variety. Okay, but if we take a k bar isogeny class, then also I can construct a compatible system. Not compatible system, it is a M compatible system. And this is the thing actually, because and here I'm using the Silverberg's result also, that if two abelian varieties are k bar isogenous, then over this field K812 B12 we have a isogeny. Isogeny will be defined on this field. Then we'll get a compatibility actually because of this dz square. Here I will take the dz square because K812 over K that divides this extension means dz. So this is compositum will also divide, compositum will divide dz square. Okay. So here I can sense L to L prime because over L we have a isogeny. If isogeny, then these are from this gives a compatible system. So I can sense here L. Okay. If I take the dz square, then you can say that because just take the FL to this side. Okay, the Frobenius V and VL. Okay, then we have the equation, right? Frobenius powers will come. So now I am taking, but right hand side is dependent on L and left hand side is doesn't depend on the this field L. Okay, so we have these equations, and then the main thing is this structure theorem. Means if we have a M compatible system, these are motivated by a similar statement for compatible system for by work of Ojeki, where he proved that if rho AL image is abelian, then we have a it doesn't have AKGL is empty for large L. Okay, that abelian thing he actually considered the power of the representation. But in general, we can define a power of a representation. But these statements we can generalize. So if we have a M compatible system, actually, if we have a infinite set lambda means and satisfying this hypothesis, this what I'm saying here. If rho bar is actually potentially coming from a potentially cyclotomic character, then actually we have rho L and this will be potentially equivalent. Okay, and we say that well weights are same. Two potentially equivalent representations. Means well weights doesn't sense with base sense actually. Hosted weight and well weights they are base sense invariant. But one more, there is something called time inertia weight. I have not defined that. But in the proof, we have to use the notion of time inertia weight and a result of Caruso. Somehow for large L, time inertia weights are bounded by actually Hosted weight, because here Hosted weight are given. The main thing is that if for large L, if I get an infinite L, yeah, okay, okay, okay. This is the main means proposition we use and means yeah, we get in a contradiction means. Yeah, these are the references.
Thanks for the talk. Is there any question or comment? If not, let's thank the speaker again.
Okay.
No, this is the slide. No, it's not the first. The slide. The point.
So the next talk will be given by Sohan Ghosh from the Harish Chandra Research Institute, and he will lecture on the pseudonality of fine-Selmer groups of function field. Please.
Thank you for the introduction. So, first, I want to thank the organizers for giving the opportunity to speak in this wonderful event. And title of my talk is, as you have seen, this uncertainty of fine-Selmer groups over function fields. I will first start by recalling Iwasawa's because zero conjecture. It's a really classical and still unsolved. So one of the key observations of Kosan Sujata in 2005 was to connect this conjecture Iwasawa, the structure of fine-Selmer groups of elliptic curves, which you will see in this slide. Then we will talk about the structure of fine-Selmer groups over general periodic Lie extensions. More specifically, we'll talk about the conjecture of Kosan Sujata again, or conjecture B, in this under the section of pseudonality. Finally, we'll talk about the status of conjectures A and B over function fields in unequal characteristic as well as an equal characteristic. I'll define all these things as we go along. So let me first give a bunch of notations. So P will be for me an odd prime. ZP is the ring of periodic integers. QP is a quotient field. And throughout this talk, whenever I say that M is a R module, I always mean that M is a left R module. And M square bracket P to the power R is a notation for the elements of M, which are killed by P to the power R. And M round bracket P is a union of all these P to the power R torsion points of M. For number field K, I will use the notation CLK to be the idle class group of K as the idle class group of K. So we know that this quantity is not a well-behaved quantity in the sense that there are many questions which are still unknown. For example, the questions like whether there are infinitely many class groups or quadratic extensions of class group is one or not is still not known. But what Iwasawa showed at the pre-primary part of class groups of certain extensions tend to follow a strict pattern. And this is precisely what this conjecture is about. We'll talk about in the next slide. Let me quickly recall what is the Slack-atomic ZP extension of a numbered field. Is zeta P to the power n with the primitive P as a unity and keyword. Sorry. And Q zeta P infinity is the union of Q zeta Pns. The Slack-atomic ZP extension of a numbered field of Q, first defined for Q and then for numbered field, is the unique extension of Q inside Q zeta P infinity, which we denoted by Q sub C by C. That's the Galois group over Q Slack-atomic over S now to ZP. So basically, draw it. So firstly, we have Q here, and we're defining Q zeta P infinity as the union of all this Q zeta Pns, and Slack-atomic ZP extension of Q, denoted by Q suffix C by C, is the unique extension of Q. This Galois group is isomorphic to gamma, isomorphic to ZP, denoting by gamma the Galois group is occurring over Q. And for numbered field K, we simply define it as the compositum of these two extensions, K and Q Slack-atomic. So this is again isomorphic to ZP. And one can show that there exist finite extensions Kns of K Slack-atomic. That's the Galois group of Kn over K is isomorphic to Z mod P and Z. So basically, this extensions line something somewhere here. And so nothing but the K Slack-atomic fixed by the open normal subgroups of the Galois group of K Slack-atomic over K. And this is isomorphic to Z mod P and Z. What Iwasawa showed is the following, that the size of the p-primary class group of this case is of the form P to the power n lambda plus mu P to the power n plus nu for n sufficiently large. And this quantities lambda, mu, and nu doesn't depend on n when sufficiently large, and these are non-negative integers. In fact, he showed it for a general ZP extension. And for Slack-atomic ZP extension, he claimed that this mu should be 0. And this is precisely what Iwasawa's mu zero conjecture is. So Slack-atomic ZP extension, this mu has to be 0. So far, the results in the detection are for abelian number fields by Pierre and Washington in 1979, it was in 1984, in which they show that this conjecture holds if Galois group K over Q is abelian, but is still open for general number fields. And the approach taken by the experts is to use abelian varieties to attack this problem. And more precisely, we'll talk about the connection of this conjecture with the Fein-Selmer group. This Fein-Selmer group is a subgroup of the Selmer group. We have seen last talk about the Selmer groups. So basically, let me recall it briefly. What are Selmer groups? So let E over K be electric curve over a field K. Now for the next couple of slides, K will be a number field. Then we switch from number fields to function fields, so characteristic P. Well, we have seen the result by model and well. And for number field K, this group, the K rational points of the elliptic curve, is a finitely generated abelian group. And for a function field, this is also true. And this first proof before this result actually were Lang and Heron. And so we also saw the definition that to prove this model theorem, it will show the finiteness of the Fein-Selmer group, which is defined as the kernel of this map from H1 GK. The GK is my shorthand for Galois group K bar over K. So GK is the absolute Galois group of G at K. So GK is Galois group K bar over K. K bar is the algebraic closure of K, as usual, and EK bar is the intorsion point of the elliptic curve EK bar, and GKB is the decomposition subgroup of GK at the prime V. KB is the completion of K at the prime V, and AKB bar are the KV part points of the elliptic curve. And the product is taken over all the primes. This was the last lecture how it is defined. And also we saw that this EK mod NEK, the weak modular group, in fact, hinges inside the Fein-Selmer group, and the quotient is the n-torsion point of the Ted-Shaver wedge group, which is defined as the kernel of this global term H1 GK K bar to put all the primes H1 GKV EKB bar. So particularly if I take n to be P, then I can show that the FP dimension of the Fein-Selmer group is greater than equal to requires upper bound on the modular length of the ends of the elliptic curve over K. And the P infinity Selmer group is defined as the direct limit of P to the power n Selmer groups over K. And now let us look at another definition of Selmer groups. So let S be a set of finite set of places of K. It contains the primes above P, the infinite places, the primes of bad reduction of E over K. And one can show that this Selmer group, and also let Ks be the maximal algebraic extension of K and benefit of set S. And one can show that the Selmer group, P infinity Selmer group, the notation I'm using is here S E slash K, is the kernel of this map from H1 Ks over K. Ks over K is again shorthand for Galois group Ks over K. If P infinity is a union of, so I change my notation here. P infinity is the union of P power torsion points of elliptic curve over Q bar. So maybe notation. And is H1 KVE, and direct sum is taken over the finite set S. So the difference here happens in the sense that you're taking the product of all the primes V, but we can show that actually we need to define it for finite set of primes, and there is a change in the Galois group here, in the global part. Now one defines the P infinity Fein-Selmer group as the kernel of this map from H1 Ks over K P infinity, direct sum V in this side, H1 KV P infinity. So obtained by giving stricter conditions on the local terms. So the difference here happens in local terms in the Selmer and Fein-Selmer groups. And one can show this isomorphic to the kernel of the map from the Selmer group to the direct sum V dividing P K with density P mod ZP. So this Selmer group is in this Fein-Selmer group is indeed a subgroup of the Selmer group, as we can see from this exact sequence, this one. And so what the cyclotomic ZP extension, the Fein-Selmer group is defined as simply the direct limit of Fein-Selmer groups over Kns, where if you recall this Kns were finite fields over K, whose Galois group was isomorphic to Z mod P and Z. Now, Courses Sujata conjectured that the Pontryagin dual of the Fein-Selmer group of the cyclotomic ZP extension, which is defined as a set of continuous homomorphisms from this group to QP mod ZP, is a finitely generated ZP module. And what they surprisingly found that this has a connection with the Iwasawa-Smigol-Zille conjecture. More precisely, what they proved is the following. So let E over K be an elliptic curve, KEP, This extension obtained by attaching the p-torsion point elliptic curve with over the field K. Assume that K, if over K is a finite P extension, then the Iwasawa's mean equal to 0 holds for case dichotomy. If I know only if conjecture A holds for contracant of the finite Selman group of case dichotomy. So this condition, like K over K is a finite P extension, is satisfied trivially in the case. For example, when the p-torsion points elliptic curve in over Q bar is already inside K. Now, next we move on to the setting of the non-commutative Iwasawa theory. So more precisely, we consider G to be a compact p-adic Lie group. It has no element of order P, and with a closed normal subgroup H, such that the quotient G mod H, which is denoted by gamma, is isomorphic to ZP. This is the kind of setting one considers when computing the non-commutative Iwasawa main conjecture. For example, in the paper of Course Fukaya, Sujata, Binyakov, and Kato. So one defines the Iwasawa algebra G over ZP as the inverse limit of ZP G mod U, where the U varies over the open normal subgroups of G, and the inverse limit is taken with respect to canonical projection maps. So in particular, suppose let us take G to be H to be trivial, and one can show that this GP gamma is a really nice structure. So ZP gamma is isomorphic to the power series ring over ZP, so ZPT. Let me define this, what is the signal ZPG module. So if M is a finitely generated ZPG module, we say that M is a signal ZPG module if the X tie groups, X tie ZPG, M comma ZPG vanishes for I equal to 0, 1. So this is one of the definitions of signality. In particular, if X naught vanishes, then one says that M is a torsion ZPG module. In addition to that, if X1 vanishes, then one says that the module is a signal ZPG module. So what was the conjecture about the structure of finite Selman groups over this extension is the following. Suppose that F be a number field, assume that conjecture A holds for E over F dichotomy. Let F infinity be an admissible p-adic Lie extension of F. So admissibility, I mean there are three conditions that I want F to satisfy. So the first condition is that I want that. So firstly is a F number field F infinity, it should contain a dichotomy ZP extension. It's condition 1. And second is that finitely many primes of F should unify in F infinity. And thirdly, the Galois group G should be a compact p-adic Lie group without any p-torsion. The first line of the last condition. First line of the first condition. Then we say that if it is admissible p-adic Lie extension. For example, there's something to the false extension, which so examples at the extension is union of, so if I take this extension, so F to be Q mu P, and F infinity we can define as union of Q mu P N. Then we should also know, and M should be P power free. So this is an example of our extension, which the admissible p-adic Lie extension. So also want this admissible p-adic Lie extension to be have as a, so the Galois group has dimension at least 2 as the p-adic Lie group. This also wants, for example, this is also satisfied in this case of Foster extension. Then they claim that the contracant of the finite Selman group of infinity is a signal ZPG module. So this is the scenario with the function number fields. Next, we'll move to function fields. So the first case is the unequal characteristic L not equal to P. So let us fix the integer, fix to integers Ln. So let L be integer prime, which is not equal to P. And F be a finite field of characteristic P. And set K to be the function field over T, over this F, finite field. Next, I will define a ZL extensions. ZL is not equal to P. And then we will, in the next slide, we will consider ZP extensions. And this is defined as follows. So first we take the finite field of characteristic P. And we know that the Galois group F bar over F is isomorphic to Z hat. So there's a unique ZL extension inside this. So this is, we know, we denoted by AP, sorry, FL here. So this is a unique extension of F inside F bar. This Galois group is isomorphic to ZL. And we define the ZL extension as the compositum of K and FL. So this is undignified to all the primes. In fact, one can show this. And one can show this is a unique undignified ZL extension of F, of K infinity. So this is a unique undignified If I take K and the compositum of these two fields, K infinity is the compositum of K field. And K, this is the unique unidentified extension of. So this is quite contrary to the number field case, because in number field case, whenever I consider the Galois S1 Galois unidentified extension is always finite. The infinity final group in this case is defined, but it now is a elliptic curve with the function field K, not no longer the number field. So one defines the infinity Selma group here over K, and analogously as in the case of the number field. And here S is the, I haven't defined S here. So S is the final set of places containing the bad primes of E over K. So one can define the final group analogously as in the case of number fields, and one can again show that this is independent of S as in a number field situation. So let us talk about conjecture A and conjecture B in this situation. So we take proof that actually the conjecture A analog here holds in the L not equal to P case, and we could find the examples where this conjecture B fails using the result of Valentino and Valentino. So the trick here is that, or the strange part is that here the Kumar map is always 0. So EKB is a equivalent mod 0, and the proof is almost similar to the number field case. So it's always 0. So we can draw, highlight it. So here the fine Selma groups turned out to be isomorphic to the Selma group, in fact, in this case, L not equal to P case. So we get some strange results. And this is one of the results of work with advisors, and it's in the preprint. Now we move on to the characteristic case. So let K equal to FT be a function field of characteristic P, and we define the final Selma group with the using flat cohomology here. So here we're dealing with the characteristic when the K is characteristic P, and the group scheme defined by P infinity is also characteristic P. So you can't use Galois cohomology here. We have to use flat cohomology. So let S be the set of final set of bases as usual, containing the basis of bad reduction of E. Then we define the final Selma group. Also, the Selma group is also defined using the flat cohomology here. So the S final Selma group we over K is defined as the contour of the map from H1. So I'm notating by H1F, it's during the flat cohomology. K here, so the notation actually is H1 flat K P infinity. Actually, it is H1 flat spec K or my P infinity, not just, it's not a Galois group anymore. It's H1 flat spec K P infinity. There is some V in S, H1 flat spec K P infinity. And there is some V not in S, H1 flat spec K V E, P infinity as outside this is. So in case of number fields, also case of function field not equal to P, one can show that this HI flat K E P infinity. So this is if K is a number field, K is a number field or L characteristic L, characteristic K is L. And also L not equal to P case, sorry. So basically, this is equal to the ethyl cohomology, ethyl group H1K, and one can further show this is isomorphic to the Galois cohomology, H1GK. But this doesn't happen for the function field equal characteristic. This fails, this result due to Milne. So it uses flat cohomology to define this S fine Selma groups. And now the ZP extension that we consider are K infinity are naive ZP extension, which is defined analogously as in the case of L not equal to P case. So basically, we have again finite field F and the unique ZP extension FP here, and the ZP extension. I'm create the compositum of this extension with K, and we get the naive ZP extension over K. And the second type of ZP extension we consider here is used by using Carless modules. So here we can get infinitely many ZP extensions. What we can show is the conjectures, analog of conjecture actually holds for both these extensions under certain conditions. Let us talk about conjecture B. So something strange happens here. So unlike the number field case, here we can produce infinitely many ZP over D extensions for any d greater than or equal to 1. In fact, for any prime P of K, we can get a corresponding ZP over D extension. I'm denoting by KBT, K to power T power P, mass fract P sub is D, for d greater than equal to 1. And this extension is signified at the prime p, and it's signified everywhere else. So its notation, latest notation is kpt. And one can show that, and we're able to show in a situation that if I take the compositum of k infinity and kdp, and suppose there's a unique prime identifies in this case, which is the case because in this extension, there's only one prime identifies in this extension, the other, and no prime identifies to k infinity. So if I'm taking this f infinity as the compositum of k infinity and kpd, and this k infinity and kpd, so f infinity. So here, no prime identifies here. Totally unidentified with all the primes. And there's only one prime identifying here. This is the extension which only one prime identifies. During this unique prime by VR, let E over K be an ordinary relative curve. That I mean that the p-torsional modulity curve is non-zero. As good reduction outside this side VR, one can show that the Pontryagin group of the final settlement group is a GPG module, whereas G is the group Galois K affinity over F, and S is the set of primes containing the set VR. And we will also extend it for the case when I just K infinity just KDP for d greater than equal to 1 under analogous assumptions. The references for my talk are the following. So my first paper with my advisors, Ramanujan Chandrasekhar, and this IISER theory for final groups of function global fields, which is in archive. And the second is my paper, also in archive recently. Thank you for your attention.